Hello guys, thank you for watching this video lecture. We want to study negative binomial distribution. It's a kind of discrete probability distribution and it is used to model the number of trials that are needed for the first success in some independent Bernoulli trials. So this tutorial covers definition, properties, mathematical formulation, practical example, and also Python coding. Let's dive in. So in the previous lecture, we studied binomial distribution, and today we want to study negative binomial distribution. In the binomial distribution, we want to model the number of success in a fixed number of trials. And in here, it consists success probability per trial. For example, number of heads in 10 coin flips. In negative binomial distribution, we want to model number of trial until a fixed number of success. In here, we have some independent trial with constant success probability. For example, number of coin flips until 3 hits. So in the case of binomial distribution, our focus is on counting success within a set limit of attempts. However, in case of negative binomial distribution, our focus is on how many attempts it takes to reach a target number of success. So binomial fixes the number of trials and counts success. However, negative binomial fixes the number of success and count trials. Binomial has a maximum limit like number of trials, but negative binomial can go indefinitely until the goal is met. Binomial asks how many successes in a set number of tries, and negative binomial asks how many tries until a set number of successes. Binomial has less variability, but negative binomial shows more spread, especially when success is rare. Binomial can be used for fixed experiments like counting yes in 20 surveys. A negative binomial suits waiting time scenario. For example, interviews until 3 hires are found. For example, in the case of finance, we can model scenarios like trading days until a target profit or credit application before finding qualified borrowers. For epidemiology, it can fit disease case count with high variability. In, for example, ecology, it can model species abundance like bird population with cluster distributions, etc. In here, we want to find the parameters of negative binomial. Once again, negative binomials model trials that are needed for a fixed number of success in some independent Bernoulli trials. So in here, we have R as the success. It is target number of success, and R is greater than 0. Then we have trials K, trials until Art success, that is our focus. Then we have P as the probability of success, and probability of success is something between 1 and 0. And we have probability of failure, or 1 minus P, that we show by Q. There are two interpretations for negative binomial. One is number of trials until R success, that is our focus. An alternative form is number of failures between our success. So here we can see the PMF and CDF, mean variance and standard deviation for negative binomial distribution. The PMF gives the probability of needing exactly k trials for our success. So we'll show Px is equal to k, combination of k minus 1, r minus 1, probability of success, probability of failure. So in this case, this combination of k minus 1 and r minus 1, this is ways to arrange r minus 1 success in k minus 1 trials, right? And this is kth as the rth result. Then we have CDF here. CDF is the probability of needing K or fewer trials. K or fewer trials. So we write again sum of the this one, right? Sum of I from R to K, combination of I minus 1, R minus 1, probability of success, probability of failure. Then we can go for mean. Mean is R by P. Variance is R multiply 1 minus P divided by P square. And standard deviation is simply root square of variance. For example, we want to roll a fair die until 3 sixes. So in this case, we can say 1, 2, 3, 4, 5, 6. This is our sample space. And probability of success is 1 by 6. And this is Q, probability of failure, which is 5 by 6. R is equal to 3 success. Probability of success is 1 by 6. Probability of failure is 5 by 6. And probability of 10 rows, it means probability of x is equal to 10 is equal to, based on this PMF equation that we have here, k minus 1, r minus 1, right? K minus 1 is 9, r minus 1 is 2, probability of success in power of 3 and probability of failure in power of 10 minus 3, right? So we can write 9 by 2 and this 1 by 6 power of 3, 5 by 6 in power of 7. Then this 9 factorial divided by 2 factorial, 7 factorial, right? And if you calculate this simple math, you can come up with 0.465. Okay, so we come for Python coding. First, we import NumPy as NP. Then also we will go for scipy.stats, and there we import negative binomial, negative binomial. And also for plotting, we will import matplotlib.pyplot as plt. Okay, now let's do the Python coding for the same example. For this one, I will go for random seed of, like for example, 42. Then I will add one list for simulated trials. Is empty list, then I will add to it. And R is equal to 3, and probability is equal to 1 by 6, right? Then 4, so counter doesn't matter. I in range of 1000 times simulation. Success is equal to 0. Later I will update it. And trials is also 0. I will update it later. So while success is less than R, because we are going to find our success, so every time my trial will be plus equal to 1. Then if np.random is less than p, is less than my probability, it means I found a success. So success plus equal to 1. Then simulated trials, I will append, right? Append this one to my trials. Okay. So I will append trial to my simulated trials. Then what is my k? K is simply NP, a range of R and 20. Okay, and PMF, I will calculate based on the equation that we have. N binom PMF, and in here K minus R, R and P, right? So this is how it works. There is some error. Trials. Okay, correct. So let's plot it. We can go for histogram. So plt.histogram, and we go for simulated trial. Simulated trial means can be range of R, like 3, and max of our simulated trials and plus 1 and density. So here we should close this one. Then density is equal to true. Alpha transparency is equal to zero point 0.8, and label we call it as simulated. So let's see what happens. Error. Okay, here we go. This is our histogram. So we can also add theoretical PMF to this one as well. So plt.stem kpmf pmf, then base fmt label is equal to theoretical PMF, right? So here you can see this is our theoretical PMF and these are our simulated. Okay, so here there is another example. An oil company conducts a geological study indicating that an exploratory oil well has a 20% chance of striking oil. So it says 20%, so probability is simply 0.2. So the question is, what is the probability that the third strike comes on the seventh well drill? This is a kind of negative binomial distribution problem because we want to model the number of trials until the third success, right? So simply we can say R is equal to 3. In this case, PMF is based on the equation that we have is equal to combination of x minus 1, r minus 1, probability of success in power of r, and probability of failure in power of x minus r, right? So our r is 3, our x is 7, probability of success is 0.2, and probability of failure is 0.8, right? So probability of 7, simply px is equal to 7 is equal to x minus 1, 6, r minus 1, 2, combination of 6 and 2, 0.2 in power of 3, and 0.8 in power of 4. 6 factorial divided by 2 factorial, 4 factorial, 0.2 power of 3 multiply 0.8 power of 4. If you do the calculation, finally you will come up with this one will be 15, this one will be 0.008, and this one will be 0.409, and after that approximately it will be 49. So I can say approximately 4.92% chance that the third strike comes on the seventh well drill. So if I want to go for expectation, I told you that E of x is equal to R divided by P. So what is R? R is 3. What is P? 0.2, which give you 15 as the expected value, right? Or mean. Then variance where x is equal to r multiply 1 minus p divided by p square. What is r? R is 3 multiply 0.8 divided by 0.2 square, and this give you 60. The mean number of wells is 15 and variance is 60. Okay, let's go for Python coding. For the oil example, suppose probability is equal to 0.2, and in here r is equal to 3. So the number of sixes, it means third strike, right? And x2 is equal to 7. This is the trial number we are interested in. It means seventh trials, right? K is equal to x2 minus r. This calculate number of failures before r success. It means 7 minus 3 is equal to 4, right? So in here we can calculate PMF is equal to n binom.pmf, and in here we get K, R, and P. Calculate PMF for negative binomial at K failure or success with probability of P, right? Then simply we can print our PMF And in here we can say PMF, and we can go up to 2F, right? So it will be 0.05. Then in the same way, we can go for mean and variance. Mean is equal to R divided by P, right? And we can print mean. We can print mean. It is 15. Then we can go for variance. Variance is R multiply 1 minus P divided by P square, right? Then we can print our variance. It is 60. And also we can go for a standard deviation is np.sqrt of variance, and we can print a standard deviation, right? 7.75. This is standard deviation as the square root of variance. For plotting, we first go for trials. Trial like a negative binomial is equal to np a range of R and 15. Array of trial numbers from R like 3 to 14 for negative binomial plot. And also we can go for PMF values, PNF values. And in here we go for nbinom.pmf. Then here we add trials R and P. Then for plotting, we go for stem plot, plot stem, then trials underscore NB, then PMF, and the rest will be the same. So we visualize probability of wells drilled until the third oil strike. In X here, these range from 3 to 14, starting at the number 3 sixes. And this y-axis is the probability for each trial number. Then there is another example. One agent resolves issues with the probability of 40%, and we want to go for calls until 2 resolutions. We show by R is equal to 2, right? So in this case, our R is equal to 2, our P is equal to 0.4, and Q is equal to 0.6, right? So on average, 5 calls, right? So 2 divided by 0.04, it's equal to 5, right? And the variance is 2 multiply Q, this is Q, divided by P square, right? Which is 7.5. For example, our R is equal to 3, and probability of success is 0.3, right? Then for K, we say K is equal to NP, a range of R and 20. PMF is equal to, we go to N binom, and in here we have PMF function. So we pass K minus R and P, right? Then we can print our PMF, print the PMF for K is equal to 10. And in here, we simply say PMF of 10 minus R. 0.08. Then also I can go for CDF. So CDF is equal to n binom dot CDF K minus R and P. Then in the same way, I can print my CDF as well. So CDF for K is equal to 10, CDF of 10R, and then you can see 6, 2. Then I can go for mean. So mean is equal to R divided by P, right? And then I can print my mean 10. Then I can go for variance. Variance is equal to R multiply 1 minus P divided by P square. and then I can print my variance 23.33. Then I can go for a standard deviation is simply NP SQRT of variance, and then I can print my standard deviation as 4.83. Then I can plot my CDF and PMF from matplotlib plt.figure. Peak size is equal to 5 and 5. plt.stem, and in K PMF, and base FMT is equal to just space, and label I call it as PMF. So this is my PMF. I can add CDF as well here. plt.plot KCDF, and I show by red and dash, and label as CDF. So this is my CDF. Okay, thank you very much for your attention. In this lecture, we studied negative binomial distribution that models trial until success. It's flexible for real-world waiting time problems, and it can be used for finance, epidemiology, ecology, and many more. Please practice and feel free to ask me your questions by leaving a comment below this video lecture. Thank you and see you in the next lecture.